Hello all of you. Welcome to 32nd lecture of the course on analysis and modeling in chemical engineering. In this week, we have been talking about numerical methods of solving equations. We started talking about linear and nonlinear algebraic equations. We discussed the iterative method of solving it, which I called direct substitution. Then I discussed about the ideas of convergence. We can have good convergence, poor convergence, oscillatory convergence, or instabilities, divergence instability, oscillatory instability. And then finally, we discussed how we can counter that by doing partial substitution. And finally, we also discussed about Newton Raphson method, that is more improved because it considers the derivatives as well. In this lecture, I will take it forward and see how we can implement that on a computer. So, I will begin with some of the fundamental ideas. So, I have discussed about Newton Raphson method, and in fact, if you think about it, it can be interpreted as coming from the Taylor series approximation of functions, which is what I want to show it, right. So, for example, if I have a function f of x, then I can write f of x plus h for a small value of h as something like f of x plus h f prime of x plus h square by 2 f double prime of x and so on. Right. If we stop at the first derivative, then we are going to have something like f of x plus h f prime of x, and therefore, we can write f prime of x as something like f of x plus h minus f of x by h, right. Now, let us look at the Newton Raphson method and just try to see, can we relate it to something like this, right. So, what exactly we did there? We set my x new as the x old value minus f of x by f of f prime of x, which is x old by x old, right. So, where is going to be my new value? New value can be assumed to be some small gap from the old value, right. So, if I set it something like x of old plus h, then Newton Raphson method gives me something like h is equal to minus f of x old by f prime of x old, right. Now, if I plug it in there, what are we going to get? If I put x equal to x old and x plus h is equal to x new, we are going to have f prime x old is equal to function of x new minus function of x old divided by x new minus x old. And now, we make a small approximation, and that is, I assume that whatever this new value of x I am going to get, that new value becomes the solution of the equation, right. So, that is my new guess. So, my new guess I am assumed to be a solution of the equation. If I do that, that means I am assuming that this term is basically 0, right, which is not the case, and therefore, we have to iterate again anyway, but I am going to assume that the new value becomes the solution. So, if I do that, that pretty much gives me x new is equal to x old minus f of x old by f prime of x old, right. So, therefore, the Newton Raphson method for one variable can be derived using the Taylor series approximation of function. Now, you can also see that when it is going to perfectly work, if for example, if you have linear function, let us assume that f of x is of the form ax plus b, and if I use Newton Raphson method for this particular case, right, what are we going to have? We are going to have something like x new as x old minus f of x old by f prime of x old, and that gives me something like x old minus ax old plus b divided by f prime of x, which is equal to a in this case, by a, and you will see if I plug it in there, I am going to get minus b by a, which in fact is a solution of the equation. If I set f x equal to 0, ax plus b is equal to 0, and that gives me x equal to minus b by a. And this worked because when we have the linear function, we do not have to worry about the second order derivatives and so on, they are anyway equal to 0, right. And therefore, in this particular case, we get an exact solution in doing just one step. But when we have a nonlinear equation, clearly it is going to take more iterations, but nonetheless, as we have discussed, the information of derivative really helps converge the solution faster as opposed to a direct iteration, direct substitution, where we do not use the derivative values. Okay. So, now I want to show you a simple code of direct substitution in Python. I want to demonstrate pretty much whatever iteration I have done in the previous lecture, and this is the very basics of Python. I do not expect that you know Python, so but you can look at this code and pretty much it is straightforward, and you can try it yourself by typing same lines in Python, right. The codes of Python which I am showing in this course, I am running using Jupyter Notebook. So, these are called interactive Python code, but that is besides the point, right. So, I also want to make inline plots, which is helpful to see like what is going on. So, I am using some library in Python called matplotlib to make inline plots, right. And every version of Python may have slightly different syntax, but more or less the idea remains that we can use a library to make plots and so on. And then since I use some mathematical function, I am using another library, NumPy library, and it is not the best way of doing a code, but I am importing that entire library. I could have written the function's name which I have importing, but if I put a star, that means I import all the functions of that library. And then also we have a matplotlib, right. So, I am doing an inline plot, but this particular library, the pyplot library, I am also importing as PLT, means whenever I have to refer to this library, I will call it PLT dot something, and you will see when it comes. And now let us say I start with some initial guess value, let us say x old is equal to 4, and I have defined some error, because ultimately I want to iterate until the error is bigger than some tolerance. But to start the loop I will show you in the next slide, I have to put some default value of error. Let us keep it a high value, right, and I also define a variable error, and let us keep it a high value so that it gets in the loop for the first time, and then within the loop I will show how we compute the error, and we set certain tolerance. So, I am going to stop when my error becomes less than this tolerance, which is pretty small to begin with. I mean, it is like probably an overkill. You do not want so much accuracy. So, you can work with even smaller even higher tolerances like 10 to the power minus 9, but I am doing 10 to the power minus 15 just as in this particular case, because we get a simple solution. And then I want to basically store the values of x and function of x. Keep in mind that I am trying to solve direct substitution, x equal to f of x form, right. So, I will have the values of x and I will have the function values, right? And essentially function values are set it into the x values. So I am storing both these values, and then whenever I start a loop, there is other preparation that we also do, and that is we have to ensure that we don't enter an infinite loop, right? What if the program I am writing is not converging, if it is diverging? What is if it is having a very poor convergence, right? What if it is into an oscillatory instability, right? So in all these cases, the criteria error less than tolerance is never going to met, right? So therefore, we need to basically also have some control on the number of iterations that I am performing. That is generally true for any iterative code, right? That we have to have some control on the number of iterations performed, right? So I am counting the number of iterations. I begin with number 1, that is the first iteration, and this is my loop to perform the actual iterations, and I am setting two conditions to be in the loop. The error, if it is higher than tolerance, then I should be in the loop. That's the reason first time I am setting a large value of error, so that I get inside for the first time, and then I will compute the error within the loop. And then the number of iterations, I start from 1, that should be less than 100. So I will just wait for 100 iterations, and I will stop if it is not converged in 100 iterations. I can of course increase this number, but just to demonstrate that I am having some control on the number of iterations, some control to avoid the infinite loops that may possibly result in this case. And I am printing the old value of x, and I am starting with a linear function, right? And I am a single variable function. X new is 8 by 9 plus 4 by 9 x old. So my f of x is 8 by 9 plus 4 by 9 x, let us say, and I append the old value in the x vector, and I append the function, the new value, in the fx vector, because I use fx to compute that function, right? And then you will see it becomes useful to print, and then I print the new value, and I also print the old value, right? And when I repeat, you will have this new value becoming the old value. Just to demonstrate that this is happening, I am doing this print, right? And in this case, I am defining the error as the absolute difference between the x new and x old, and finally I am setting x old to x new. So for the next iteration, whatever value I have got, the new value I have got becomes the old value for the next iteration, and I increment the counter by 1. So after one iteration it becomes 2, after 2 it becomes 3, and so on, right? It will keep on going, and I will keep on doing it until I have 100 iterations, or I reach the condition of error less than tolerance. So both the conditions, whatever I have given here, must be met in order for the loop to continue. So either the error becomes less than tolerance, that means we reach convergence, or the number of iterations become higher than 100. In that case, we reach the maximum number of iterations we have given, and accordingly later on I am printing if the number of iterations becomes 100, then I simply say that maximum number of iterations reached, or I say solution converged in so many steps. And now finally I want to plot it. So I want to have some labels of the plot, the x label, the y label, but essentially I am plotting x and f of x. F of x is the new value of x I am getting, and also showing some legends, and you will see when you see the plot. Okay, so this is how the iteration goes for this particular case. I start from x equal to 4. It keeps on going, and probably by here it has already reached close to the solution, that is 1.6. But then it will keep on doing it because my tolerance was kept to be very small. And you see that I have not showing all the values of x printed, but towards the end it looks something like this, and you see I want a value 1.6, but it is pretty much close to that. The error is less than the tolerance in this case, and we say that the solution converged in this case in 45 steps. Of course, if I set tolerance to be somewhat larger, then I would reach in much fewer steps. So this is how it looks like. So this is my f of x line, and this is my xc is equal to fx line, right? And basically I start from here, so I am doing something like, let's say I start from here, so I go from here to here, then I go to this, come here, 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 and in 45 steps I reach the true solution, just the way that I have shown in the previous lecture. Okay. Now I am showing another case where I have oscillatory instability for this simple quadratic equation. My f of x now is x square minus 3. This is, if I put 2 stars, that gives you the power sign in Python. So x square minus 3 is this. And now you see I start from, let's say, minus 2, right? So I go to the function and I come to the line x equal to fx, and then I get the new value, that is 1. And now from here I go here and I again hit minus 2. And you see now we have reached an infinite loop. I am going back and forth, back and forth, back and forth, back and forth, and clearly we will stop after 100 iterations, because I have set a way to avoid this happening. Once this starts to happen, then I am going to stop after 100 iterations. And you see the values were getting printed, minus 2, 1, minus 2, 1, minus 2, 1, and so on. Okay. Now, in this particular example, whatever example I had, I want to see whether partial substitution helps in this particular case, right? So let's see how we can avoid this problem by doing this partial substitution. So again, I have a very similar code, except few changes I have made. So I define a variable alpha, that is between 0 to 1. So I am doing under relaxation. And then again I have this loop, and now I have modified this function as the following. So we have something like x new into is equal to some alpha times the function value, whatever we had earlier, plus 1 minus alpha times the old value of x. So this will make a partial substitution, and everything else pretty much remains the same in the code. And now what you see is, like, let's say if I start from the initial value of 1, then I can see that we are going towards the convergence in this case. In this case, we have two roots, minus 1.3 is one of the roots. And after long enough, we see that it is converging in like 67 steps, right? So now you can see whatever problem we had with the oscillatory divergence, that problem is not appearing now, because we have defined an under relaxation with an alpha variable. Again, we can play with the alpha variable to see what is the maximum value of alpha we can use, because I mean, as we make alpha lower, it will be more stable in some sense, but at the same time it will take more time. And you can see how the plot looks like. So I start from somewhere here, and now I am going towards the solution, unlike kind of oscillating around the true solution value. I can also use the Newton Raphson method for this case, but now I need information regarding the derivatives, right? So we have now the function, and now I want the function written in the way of f of x. So we had the function as x square minus 3 is equal to x, but now I write it as x square minus x minus 3. This is my f of x, and f prime of x is equal to 2 of x minus 1, right? So I have defined the function value, I have defined the f prime value, right? And here I use the Newton Raphson method. My x new is equal to x old minus f of x old by f prime of x old. that's exactly getting implemented here. And then I go ahead and do everything else similar to whatever I have done. And you see, I reach the convergence in like 8 steps, right? You see what we have done here, right? So basically, we have been able to basically use derivatives and get the convergence in much fewer steps by using the Newton Raphson method in this particular case. Okay, so now let's say I want to extend this idea and to like multiple set of equations, right, rather than just one equation. Right? Clearly, for linear equations, it is going to be easy. For non-linear equations, it's going to be hard, right? So for linear equations, I may have some different methods. For non-linear, I may have different methods, right? But the first thing is, how do I write the equations first, right? So let me assume that we have, let's say, n variables x1 to xn, and accordingly we have n equations f1, f2, fn. These are the functions of the n variable. F1 is a function of all x1 to xn, f2 is a function of all x1 to xn, right? So we have n different equations, and I can write it in a vector form where now I have a vector of functions which is essentially a functions of this x, which is now a vector, which is a vector of unknowns, right? That is right here. So I define a vector of unknowns and I define a vector of those functions. We will take examples later. And now, if the equations happen to be linear, what it can be shown that this can be written in the form something like a dot x equal to b, where a and b are like constant matrices. It only contains constant values, right? Provided that the functions are all linear, we can write in the form ax equal to b, where a is a matrix but containing only constants, b is a vector containing only constants, right? And in that case, I can do simple matrix manipulation. I can write x equal to a inverse of p, and I have the solution of the equation, right? And there are methods to solve those kind of equations. There is something called Gauss elimination method. There is something called Gauss-Seidel method, which is iterative in nature. This is the iterative method for this. Gauss elimination is rather straightforward, right? And I will not discuss in that in much detail, except I will discuss something for the tridiagonal matrices called Thomas algorithm, which I will show later, right? But what if it is nonlinear? In that case, we are going to have something that does not meet this, right? So this idea of computing the inverse of matrix, it is not going to work, right? And I will show you how to counter that kind of a problem, right? But let's first look at a linear set of equations. Again, let's say I go back to this equation. How can I represent in the vector form? I can write unknown vector x as x and y, and then I can write this set of equations in the following form: ax is equal to b, where b is equal to 2, 4, and x is xy, and a is going to be something like 2, 3, and 3, 2. You see, by matrix multiplication, in matrix multiplication we multiply rows with columns, right? So in this case, the first row I will multiply with the only column here, and we get 2x plus 3y, which is my first equation, that is equal to 2. And then I multiply the second row with the same column xy, and we get 3x plus 2y is equal to 4, right? How do I solve it? I do it by doing x equal to a inverse of b. And now the question is, how do I find a inverse? One of the ways of doing it is noting that a into a inverse is equal to my identity matrix. So we have 2, 3, 3, 2, and let me put something here, A, B, C, D, that is equal to 1, 0, 0, 1, and using this equation I can find the value of A, B, C, D, and therefore I will have the expression of A inverse, right? And once I have the expression of A inverse, I can go ahead and do it, right? Now you can see for yourself that this will give you 4 equations. This is not probably the best way to find inverse, but how do I get the 4 equations? The first equation is multiplying the first row with the first column here, that gives me 2a plus 3c is equal to 1. Then the second equation is first row into second column, that will be 2b plus 3d is equal to 0. Now the third equation is second row into first column, that is 3a plus 2c is equal to 0, and then second row with second column, that is 3b plus 2d is equal to 1, and we can solve this to get the A inverse. So with that I conclude this lecture. In this lecture I have demonstrated you how to write the code for different numerical schemes for solving of linear equations. In the next lecture we will take more examples and we start discussing the ODEs and PDEs. Thank you so much.